Air gaps are in magnetic circuits for very, very good reasons. There are air gaps in magnetic circuits because a lot of magnetic circuits are actually doing something. They're actually making something move, and it's amazing. The premise of a lot of our electric machinery is moving parts, but those parts are moving based on forces that are created in the other parts. So, for example, a motor has a rotor and it has a stator, and the rotor moves independently of the stator, and in between the rotor and the stator is the poles of the stator is this force that is wonderful and miraculous and is invisible, and it's actually creating physical things to move, and that force is the force of magnetism. So it's in motors, meters, speakers, relays, etc. We're actually using magnetism to make things actually to move mechanical objects that have mass, which is incredible if you think about it. So these air gaps are what allow the space to move. Sometimes we even increase the reluctance by putting in an air gap in order to prevent saturation. So let me show you what that means. If we remember our BH curves, our BH curves are the relationship between the flux density, and the magnetic field strength of a magnetic circuit. Here's the flux density and magnetic field strength, not really of a magnetic circuit, but of a magnetic material. And if we remember, then with density, with flux density, the density of the flux, it's the amount of lines of force between a cross-sectional area. So as that increases, we get more magnetic field strength, like a stronger magnetic field. But that's only to a point. We can't go on to infinity and make a stronger and stronger and stronger magnet, because that circuit or that material gets saturated at some point. So this is called magnetic saturation. And when we get to magnetic saturation, the relationship between magnetic field length or magnetic fields, flux density and magnetic field strength, rise over run, is a slope, right? That slope is permeability of the material. So permeability is flat here at saturation, and that's not good. It's not very permeable. We want to welcome the lines of flux, right? We want to welcome the lines of flux. So we want permeability to be high, rise over run. We want it to be as high as possible. Where'd I go here? So sometimes we put a gap in a magnetic circuit so that we could go. Sometimes if we don't have a gap, we'll be way over here and we will be less permeable, and we've kind of ruined our magnetic circuit. So sometimes we add a gap so that our permeability is in this range. Add gap. All right, so the slope goes into this range where we welcome lines of flux. And if you don't know what I'm talking about, then you're going to have to review what permeability is. What flux density is, and what magnetic field strength is. But sometimes gaps are added to prevent going up higher on that BH curve. And how does it make us not go higher? Well, it makes us not go higher by increasing surface area. So we put a gap, and don't get me wrong, most of the reasons why we have gaps are so that we have space for conductors to move, but we also put a gap in so that we increase the reluctance. Because reluctance is directly proportional to 1 over the cross-sectional area. And when we add a gap, we increase the cross-sectional area. Therefore, we decrease the reluctance. If we decrease the reluctance, then we're going to increase the cross-sectional area, so we're going to increase the reluctance. Sorry, must be a function of just area. And so if we increase the area, then we are going to increase the reluctance. So we will be less permeable. We will be more reluctant, less permeable. We will be going this direction on the BH curve. We will decrease the flux that's developed, right? Or decrease the number of lines of flux that get developed. Or at least decrease the flux density, and to decrease the flux density means that we are increasing the slope. So we have become more welcoming, more reluctant, and hang on a second, we're going to increase this total flux. Oh, so sorry. Yes, we want to decrease permeability, which brings us, and the reason why this increases permeability here, I was just stuck with why this increases permeability. It increases permeability because we went from here with the flat section of this curve down to here, which is the sloped section of curve. So we did decrease flux density, which increases permeability. All right, so we've added that gap to increase permeability. So it's very important that we know the relationship is that with an increase in surface area, we increase the reluctance, therefore we decrease this flux density, and decreasing the flux density brings you down on this on this BH curve, which brings you to a slope rise over run that is going to be greater than it was before, which makes you more welcoming to flux being established, which is a beautiful thing. So what I was describing here is this part, is how this part works. All right, so how do we make something with the gap that we've added just to increase the total reluctance? Well, we can't just have a gap there then, right? So we use fiberboard, or we use plastic, or we use brass to make an air gap. And all lines must pass through the air gap. So what we have done is basically what I'm showing down here is that every piece of our lines of flux is going to go down, and they are going to repel each other. So the lines of flux in the middle are just going to go straight down, but the lines of flux on the outside are going to repel each other. Why do they repel each other? They repel each other because the properties of magnetism are that lines of flux tend to want to be away from one another unless they are encouraged into a piece of iron. So in this case, This one goes straight through, but these ones are encouraged to stay inside this iron. They love it. Once they're in free space, they say, oh, get away from me. Oh, get away from me. And they repel one another. That gives us what is called fringing. So the lines of flux actually fringe out. They do not do this. They do not go in. They go out. So we'll just erase this whole thing. We'll erase this whole thing. They do not come in. They go out. All right. Now, what is the effect of them fringing out? Well, I don't know what this cross-sectional piece looks like, but let's say this is a square cross-section. So let's say this is a square cross-section, and we're going to look at the cross-section in purple here. And we'll see how this affects our math. So the cross-section of the iron piece, just looks like this. It's, let's say it's square. Let's assume it's square. And let's say it has a width W. So this is the cross-section, basically A of iron. And it's W by W. And I'm going to assume it's square. Here's my square cross-sectional piece. So that's this here. It's area of iron. And then if I take a cross-section in the middle where this, where the magnetic lines of force are repelling each other, then they'll be out further. So yes, this magnetic line of force would be inside, but this one used to be over here and now it's over here. So it used to be over here, but now it's over here. Same with this one. Used to be over here, but now it's over here. Used to be over here, but now it's over here. So what we have is, just 1 second. Okay, so what we have then is these magnetic lines of force that are going through the gap are actually bigger. Or the cross section that they take up is actually bigger. So it's a larger area, but it's the same number of flux lines. So therefore, flux density has decreased and we have moved down this flux density curve. Flux density has decreased, so we've moved down the flux density curve. So that's what this new cross section looks like. Why does this matter? This matters for a few reasons, because we know we take cross-sectional area all the time and we stick that in some calculations, don't we? We stick that in our reluctance calculations and our permeance calculations, which is 1 over reluctance. Now, how much larger is this cross-sectional area is the question. So the cross-section of the gap is larger than the cross-section of the iron. It is the cross-section of the fringed portion of space. So here is the fringed portion of space here in green. It's poking out wider than the iron. It is calculated by adding the length of the gap to the critical dimension. So what you have to do is look at the critical dimension. The critical dimension means sort of the, the dimension that most defines the object. Critical dimension here is W, and it's W in both directions. So it's defined by taking the critical dimension and then adding the length of the gap. So I want to add the length of the gap to the critical dimension. So I want to now have the length. Length is equal to W plus gap length, and width is equal to W plus gap length. So if I were to draw that again, here is A of iron, and here is A of gap. And I'm going to call this W, and I'm going to call this W. And if I want to label what's going on around there, then this gap here, this increase in dimension, has to total, in the x-axis, it has to total the length of the gap. So this is 1/2 gap length. And this is 1/2 gap length. Similarly, this is 1/2 gap length. And this is 1/2 gap length. So if I were to calculate the area of iron, it would be W times W. That's how you calculate area, length times width. If I were to calculate the area of the gap, it would be W plus something times W plus something. And the plus I would add is 1/2 gap, 1/2 gap times 2. Times 2, because I did it once and I did it twice. So it's times 2. If I want to show the 1/2 gap over here from this view, it looks like this. This is 1/2 of the gap length, and this is 1/2 of the gap length. Now, where is the actual gap length, though? How do you get the actual gap length? Well, it's how big the gap is. How big is this gap? This gap, it's like the thickness of the gap. This is the gap length. Gap length. So here's the gap length. I put half of it on this side, and I put half of it on this side. I put half of it on this side, and I put half of it on this side. So my critical dimension is width, and I have added one gap to that width. So I can simplify this formula and say it's width plus gap length times width plus gap length. So that's how we deal with the gaps. Now, I don't recommend that you memorize a formula for that. I recommend you look at every different problem, and then you figure out what the critical dimension is, and then you add one gap length to that critical direction. It's like padding the area by that critical dimension, padding the area around that critical dimension by a gap length total, which means a half gap length all the way across. And if I can show you what I mean here by that. If I show you what I mean here by that, let's just say that I now have a circular cross section. Let's say I have a circular cross section. Then the circular cross section, let me do that in a different color. That circular cross section would, let's say it looks like let's say a circular cross section is going to look like this. Whoops, of steel. Then the gap would look like this. The gap would look like this. And the critical dimension in this case, in a circular cross section, the critical dimension in a circular cross section would be the diameter, right? And that diameter then would have to increase by total gap length. It means that there would be 1/2 gap length on this side, and there's 1/2 gap length on this side. So then the diameter has to add 1 full gap length in order to calculate the cross-sectional area of the part that has the fringing. So what we've done then with a gap is that we've fringed out those magnetic lines of flux. And with them being fringed out, we have increased the cross-sectional area. Because we've increased the cross-sectional area and we haven't increased the number of lines of force, we have decreased the flux density. Since we've decreased the flux density, we have pulled ourselves down the y-axis on the BH curve. Pulling ourselves down the y-axis on the BH curves gets us to a permeability that is higher than it would be in a saturated region. It also lets us get to a higher magnetic reluctance, and in effect, the entire circuit is going to be less reluctant. Now, in the example, we have to explore what this means to our math. And let me show you very quickly what it means to our math. Is that previously we would calculate this as a reluctance. This is the reluctance of iron. And then we would calculate this as a reluctance, iron rotor. Now we need to calculate the gap as a reluctance. And it is going to be more reluctant than the iron. So what we've done in introducing a gap to this circuit is we can no longer just calculate reluctance. We need to now calculate this as a series magnetic circuit where our iron is calculated one way and our gap is calculated another way. This R gap is going to have a higher cross-sectional area. It's going to have a higher reluctance. It's going to have a higher, well, it's going to lead to a higher permeability. And all of these effects are going to show up in reluctance, and then we will have to add these as series to our gap. And so that's the effect of adding a gap into our magnetic circuit, a whole bunch of increase to our calculations.